Here's another sample problem on vertical parabolic curves. First, let's identify the given information. It is clearly stated that the curve is unsymmetrical. We are also given the values of the back tangent and the forward tangent. Recall that in a parabolic curve, the back tangent represents the first grade, while the forward tangent corresponds to the second grade. Next, the lengths of the curve are given as 40 meters on the left side and 60 meters on the right side. The station at the PVC is 7 plus 290, with an elevation of 110 meters. Additionally, an outcrop is encountered at station 7 plus 310 with a ground elevation of 108.40 meters. To locate the outcrop from the PVC, we subtract the stationing of the PVC from the station of the outcrop. This gives us a distance of 20 meters from the PVC. Now, the first requirement of this problem is to determine the height of fill needed to cover the outcrop. If we visualize the elevations at the outcrop, at the PVC, and at the point on the curve, which we will denote as h, we can see that the height of fill is obtained by subtracting the elevation of the outcrop from the elevation at point h. Since the elevation of the outcrop is already given, our next step is to determine the elevation at point h. To determine the elevation at point h, we begin by constructing a triangle from the reference station, which is the PVC, with its base extending to point h. After that, we will determine the vertical distance from the top of the triangle down to point h. As identified earlier, the distance from the PVC to the outcrop is 20 meters. Now, let's solve for the first triangle. The slope corresponds to the back tangent, which is 5.5%, and the base is 20 meters. The unknown is the height of the triangle, which we denote as y1. Using the slope relationship, y is equal to 20 times 0.055, which gives a height of 1.1 meters. Next, we determine the value of y2 using the parabolic relationship. The equation can be expressed as y2 over the square root of 20 is equal to h over the square root of L1. However, the value of h, which represents the height of the curve, is not yet known, so we need to compute it first. For an unsymmetrical curve, the height of the curve is given by h is equal to inside parenthesis of g1 minus g2, then multiply it to L1 and L2, over 2 times the summation of L1 and L2. Substituting the given values, we obtain a curve height of 1.68 meters. Now, we can proceed to solve the equation based on the parabolic relationship. By substituting the known values, we obtain y2 is equal to 0.42 meters. To determine the elevation at point h, let's refer to the illustration. Starting from the reference elevation at the PVC, we move upward by the height of the first triangle, and then move downward by the vertical distance y2. This leads to the equation, elevation at h is equal to the elevation at PVC plus y1 minus y2. Substituting the given values, we obtain an elevation of 110.68 meters. Now, to determine the height of fill, we subtract the elevation of the outcrop from the elevation at point h. Substituting the values, we get 2.28 meters. Therefore, the required height of fill is 2.28 meters. Now, for the second requirement, we need to determine the elevation at station 7 plus 330. First, let's identify where this station lies along the curve. We subtract the station at the PVC from 7 plus 330, which gives us a distance of 40 meters. Referring to the illustration, this location corresponds exactly to the station of the PVI. Now, let's construct a triangle starting from the PVC. After that, we will determine the vertical distance from the PVI down to the curve. From the illustration, this vertical distance from the PVI to the curve is equal to h, which represents the height of the curve. From the illustrated triangle, y3 represents the height, with a slope of 5.5% and a base of 40 meters. Using the slope relationship, y3 is equal to 40 times 0.055, which gives the value of 2.2 meters. From the parabolic curve, the elevation at station 7 plus 330 can be expressed as elevation at station 7 plus 330, which is equal to the elevation at PVC plus y3 minus h. Substituting the values, we obtain an elevation of 110.52 meters. Therefore, the elevation at station 7 plus 330 is 110.52 meters. Lastly, for the third requirement, we need to determine the elevation of the highest point on the curve. To do this, we must first identify the location of the highest point. For an unsymmetrical parabolic curve, we use a criterion to determine whether the highest or lowest point lies on the left or right side. The expression L1 times G1 over 2 is compared with the height of the curve. H. If this value is less than h, the highest or lowest point is located on the left side. If it is greater than, then it lies on the right side. Substituting the given values, we obtain 1.1, which is less than the height of the curve, 1.68. Therefore, the highest point of the curve is located on the left side. Now, using the formula for S1, which is G1 times squared of L1 over 2 times h, we substitute the given values. This gives us S1 is equal to 26.1905 meters, which represents the distance from the PVC. Next, let's visualize how to determine the elevation of the highest point. We construct a triangle from the PVC, then consider the vertical distance from the top of the triangle down to the curve at point HP. We denote the height of the triangle as y4, and the vertical drop as y5. To solve the triangle, we use S1 as the base, a slope of 5.5%, and y4 as the height. Thus, y4 is equal to 26.1905 times 0.055 is equal to 1.4405 meters. Then, using the parabolic relationship, we express y5 over the squared of S1 is equal to h over squared of L1. Substituting the values, we obtain y5 is equal to 0.7202 meters. Now, based on the illustration, we can form the equation for the elevation at the highest point. The elevation at HP is equal to the elevation at the PVC plus y4 minus y5. Substituting the values, we have elevation at HP equals 110 plus 1.4405 minus 0.7202, which gives 110.7203 meters. Therefore, the elevation at the highest point of the curve is 110.7203 meters. And that completes our solution for this problem on vertical parabolic curves. Try reviewing the steps and solving a similar problem on your own to strengthen your understanding. Keep practicing, and I'll see you in the next video.